Hello everyone, in this video we are going to talk about the polarity of bonds as well as polarity of the molecule, right? So let's start. So as we know, there are two types of bonds. We have covalent and ionic bonds, right? And covalent bonds can be non-polar or polar, whereas ionic bonds are always polar because we have a complete separation of charges. You can see we have a plus charge on sodium and a negative charge on chlorine, so that makes chloride ion and sodium ion. So since there is complete charge separation, this molecule is always polar, right? Whereas in covalent molecules, the covalent bond can be polar or non-polar. If it is, so most of the molecules that are that have the same kind of atoms, you can see both the chlorine atoms are same, so their electronegativity difference is 0, right? 0 electronegativity difference, meaning this covalent bond is non-polar, right? Both these atoms are same, so they have equal electronegativities and they pull on the shared pair equally on both sides. So shared pair lies in between the two atoms. So we call this equal sharing. So this is what we call equal sharing, because both atoms have same electronegativity, so the shared pair lies in between the two atoms. Whereas in polar covalent molecules, the sharing is unequal. So this is unequal sharing. So this bond lies closer to the more electronegative element, which is chlorine. So if you check the electronegativity difference between hydrogen and chlorine, chlorine is more electronegativity negative because the electronegativity increases left to right. See, chlorine is right here on the extreme right hand side of the periodic table, and hydrogen is here. So chlorine is way more electronegative than hydrogen, right? So the shared pair kind of lies closer to chlorine. So that gives a partial negative charge to chlorine and a partial positive charge to hydrogen. See, chlorine has a partial negative charge, which is denoted by this symbol delta, right? So this is what we call delta. So delta negative charge and delta positive charge. So this unequal sharing leads to the polarity of the bond, and the direction of the polarity is shown by drawing an arrow from less electronegative and pointing towards the more electronegative element, which is chlorine here, right? So we always draw the polarity, the direction of the polarity like that, right? So this is partial charge. Now in ionic compounds, there is a complete charge on the ions, the positive charge and a negative. Whereas in polar covalent molecules, it's a partial charge, right? So now let's see what kind of molecules, what kind of covalent molecules are polar and what kind of covalent molecules are non-polar, right? So non-polar covalent bond occurs when there is equal sharing. When can we have equal sharing of the electrons? So usually all the diatomics. What are diatomics? Remember, horses need oats for clear brown eyes. All those elements that exist as diatomics are given by this mnemonic. So oxygen, nitrogen, chlorine, fluorine, bromine, hydrogen, iodine, all these exist as diatomic molecules. What are diatomics? Two atoms bonded together, same atoms, right? You can draw the lone pairs. So this is how oxygen looks like, right? Sorry. And then this is how nitrogen looks like. Each nitrogen has 8 electrons, right? And each oxygen has 8 electrons, right? There's a double bond and then there's a triple bond, and then this is how chlorine looks like. So they are all diatomics, right? And then hydrogen is happy with 2 electrons. So all the diatomics are always non-polar. Why? Because there is equal sharing of the electrons that make the covalent bond by the 2 atoms which have the same electronegativity. The electronegativity difference is 0 because the 2 atoms are same. So the diatomics always have a non-polar covalent bond. And always remember, these molecules are always symmetrical, right? So any molecule that is symmetrical, where there is equal sharing, what do we mean by symmetry or symmetrical molecule? Means there is equal sharing. The sharing is equal between the 2 atoms that make the covalent bond. They are always non-polar. Okay? And all the symmetrical shapes are those shapes when there is no lone pair on the central atom. Those shapes are always non-polar. Excuse me. So we went over all the non-polar shapes in class. So whenever you see these AXE formulas, so if you see all the AXE formulas, A stands for the central atom, X stands for the bonded atom or the outside atom, right? And E stands for the lone pairs. So all these shapes, when X atom is same, right? Like BF3, right? So BF3 has AXE formula AX3, right? So there are no lone pairs on the central atom, and hence this is a non-polar molecule. So all these shapes, AX2, AX3 which is trigonal planar, AX4 which is tetrahedral, AX5 trigonal bipyramidal, right? 3 in one plane of a triangle, and then 1 on top and 1 on the bottom. And then AX6 which is octahedral. All these shapes, when X atom is same, like PCl5, right? And CH4, BF3, right? CO2. All the X atoms are same, and then there is no lone pair on the central atom. So this is the condition. No lone pair on central atom. This is the first condition, right? There should be no lone pairs on the central atom. And the second condition is X atom is same, right? So whenever you see this shape will always be non-polar. Okay. Now let's consider the effect of lone pairs on the geometry. So lone pairs on the central atom, they make the molecule unsymmetrical, right? And unsymmetrical molecules are always polar. So lone pairs, when they are present on the central atom, they destroy the symmetry of the molecule and make the molecule unsymmetrical, and hence the molecule becomes polar, right? So here are some of the examples of the Vespers chart, right? So you have to memorize these examples. So all these shapes, when AXE formula does not have an E in it, right? So this is steric number 3. This is steric number 4. This is steric number 5. This is steric number 6. All these shapes, they do not have any lone pairs on the central atom. So they are always symmetrical. So all these shapes are always symmetrical. And hence they are always non-polar, right? So you have to memorize that. So what is this shape? This is trigonal planar. This is AX4 is tetrahedral, AX5 is trigonal bipyramidal, and AX6 is octahedral. So all these shapes are symmetrical and hence non-polar because all the X atoms are same, and then there is no lone pair on the central atom. Now whenever a lone pair is present, lone pairs on the central atom destroys the symmetry. So whenever a lone pair is present, now AX3, we are going to replace one bond pair with a lone pair. So the formula becomes AX2E, right? So let's see steric number 4. So steric number 4, AX3E, steric number 3 is trigonal planar when there is no lone pair, right? Now this is how trigonal planar shape looks like. When you take one bond pair and replace it with a lone pair, so I can put a lone pair here. Now there are two bond pairs and one lone pair. Lone pair on the central atom destroys the symmetry. So this molecule becomes unsymmetrical, right? So this is unsymmetrical, and hence bent shape is polar. Okay. Now in trigonal pyramidal, we replaced one bond pair with a lone pair, and then it becomes unsymmetrical and hence polar, right? So this trigonal planar is symmetrical and this is non-polar, right? And now let's consider steric number 4. AX4, when all the X atoms are same, the shape is symmetrical. So this is symmetrical and hence polar, right? But when we replace one bond pair with a lone pair, look, we can take this part out. You can take this part out and it kind of looks like a pyramidal shape, right? So one bond pair replaced by a lone pair, right? On the one lone pair on the central atom. So the AXE formula is AX3E, and then the shape is unsymmetrical. So this is an unsymmetrical molecule because there is a lone pair on the central atom, and hence trigonal pyramidal shape is polar. So tetrahedral is non-polar. I'm sorry. So this is non-polar, right? So this shape is polar because this is symmetrical. And then if you replace another one with a lone pair, right? Now there are two lone pairs. Two of the bond pairs in the tetrahedron are gone. So there are two lone pairs now, and this shape is bent. This is unsymmetrical because there are two lone pairs on the central atom, and hence bent shape is always polar, right? Because the lone pairs, they push the bond pairs away from them, and then this bond angle decreases. So this is less than the regular tetrahedral angle of 109.5. Okay. Now we can see the same thing with the trigonal bipyramidal shape. When all the X atoms are same, right? This shape is symmetrical. Trigonal bipyramidal is symmetrical when all the X atoms are same, and hence this is a non-polar shape, right? But when you remove the bond pairs with a lone pair, for example, if you remove this one right here, the shape becomes like a seesaw, right? Whenever you remove a bond pair from the trigonal bipyramidal shape, you always do that from the plane of the triangle. So I took one bond pair from the plane of the triangle. The third one in the triangle is gone now, and it's replaced by a lone pair, right? So now this shape is unsymmetrical, and hence seesaw is a polar molecule or a polar shape. Okay. Let's see the same static number 5, right? This time we took another one out from the plane of the triangle. So now these two are gone, right? So the two from the plane of the triangle are gone. Now the triangle kind of looked like this, right? So there are 2 lone pairs now and 3 bond pairs, right? So this is AX3, 3 bond pairs, and E2, 2 lone pairs, right? So this is a T shape. Whenever there are lone pairs on the central atom, they always make the molecule unsymmetrical, and hence it's a polar molecule, right? Again, linear, we have 3 lone pairs. Linear shape, whether it's polar or non-polar, that could be tricky. If both the atoms are same, X atoms are same, then it's going to be symmetrical, and hence it will be non-polar, right? So linear shape is non-polar when there are 2 atoms on the same atoms on the 2 sides. Octahedral is symmetrical when X atoms are same, and hence non-polar, whereas all the distortions with a lone pair, so there's one lone pair here, when you take out a bond pair from the octahedral shape, always the axial ones go first, right? So one of the axial atom goes, and then there's a lone pair. So this kind of looks like a pyramid that has a square base. So this is a square base, and then if you join this to all the equatorial atoms, it kind of looks like a square based pyramid. So square based pyramid, this is unsymmetrical because the individual polarities do not cancel out. So this is a polar shape. Square planar with 2 lone pairs, one on top and one on the bottom, right, is also non-polar because we have a symmetry here, right? T shape is polar and linear depends on the type of the atoms, right? So square pyramidal is polar, and then the other ones are non-polar. Okay, so let's do some other examples, right? So like I said, all these shapes that have a lone pair, they always are polar, right? And then you need to know their names. So AX2E is static number 3. AX2E is bent, right? So this is bent. So this is bent. And this one, AX3E, is trigonal pyramidal. AX2E2 is bent, right? So these all are polar shapes. They are all polar, right? And then AX4E is seesaw. So this is seesaw. This is polar, and then this is T-shaped, and then this is linear, right? And then here it is square pyramidal. This is square planar, and this is T-shaped, and this is bent. Sorry, linear, right? Linear shape, when both the atoms are same, they are always non-polar, right? Now those non-polar molecules, we already talked about the symmetry, right? Molecules that have different X atoms are unsymmetrical. They could be polar. For example, both these molecules, they have tetrahedral shape. They are both tetrahedral, right? So these are also tetrahedral. They all are tetrahedral, right? But these molecules are non-polar, So let me draw one. So this is how CH4 looks like. So this is tetrahedral, right? And all the atoms are same. Since carbon is slightly more polar, so this is the direction of the polarity towards the carbon atom. So this is how I draw the dipoles, individual dipoles, right? So all of these, they kind of make the molecule symmetrical. Hence the individual dipoles cancel out and the molecule is non-polar, because all the X atoms are same. X is same, right? So the individual dipoles, they cancel out. So this one cancels out with this one cancels out with this, right? Whereas if we have a tetrahedral geometry or any AX4, AX5 and the X atoms are different, for example CHCl3, if I draw CHCl3, so it's going to look like this. So one Cl here, another here and another here, right? So the direction of the polarity, bond polarity, is like this, right? Because Cl is more electronegative than C, so the direction of the dipole is in this direction towards the chlorine. Now, and then this is towards carbon, right? So you can see there's a net dipole moment in this direction, right? So molecule is heavy in electron density around the chlorines, right? So that makes this molecule unsymmetrical, even though it's tetrahedral, right? But all the X atoms are not same. There should be at least one different atom. X is not same. So that makes the molecule unsymmetrical and hence these molecules are polar, right? So tetrahedral or any AX4 type, when all the X atoms are not same, then the molecule becomes unsymmetrical and hence they are polar molecules. So there's net direction of the dipole moment in this direction. Okay, hope that video was helpful, and I'm gonna see you in the next video where I take more examples, how to tell the hybridization and how to draw the Lewis dot diagrams and tell whether the molecule is polar or non-polar.